Hi Pre-Calculus Honors, these are Notes 9.4 Day 1. Our objectives: be able to use sigma notation to describe arithmetic and geometric sums, be able to find some finite sums of arithmetic and geometric sequences, and be able to find sums of convergent geometric series. So we're going to start with summation notation. The capital Greek letter sigma is a notation for summation. It means find the sum. So what we're going to do, go ahead and pause the video and read the information in the blue box, and then we'll find the sum for number 1. All right, so first of all, I think it would help if we find the terms of the sequence. So notice our index of summation. You would start with k equals 1, and you would get 5, and then this sigma means the sum. So then you're going to add 1, so you would say k equals 2, and then you're going to add 1 to that, and you get k equals 3, and the index of summation says start with 1 and end with 3. So you end up with 5 plus 10 plus 15. So if I want to find the sum is 30. Go ahead and pause the video and try part B. I did. Did you let k equal 6? Because our index of summation through this time started at 6, and then we add 1, and 7. Again, we're using integers. Then we add 1 and we get 8. So notice 6 squared plus 7 squared plus 8 squared is 149. And something that's very important to realize is that I know that their index of summation started with k equals 6. It did not start with 1 this time. However, k equals 6 yielded it would yield the first term. And then k equals 7 gives you the second term. And k equals 8 gives you the third term. Okay, so let's take a look at the next one. So this time we're going to let k equal 0, then k equal 1, then k equal 2, and then k equal 3. So let's think about it. If you let k equal 0, you have cosine of 0. Then with k is 1, cosine of pi, then cosine of 2 pi, then cosine of 3 pi. So go ahead and pause the video and find the sum. Cosine of 0 is 1, the cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1, so you end up with 0. Go ahead and pause the video now and think about what that means for part D and E. If we start our index of summation, we start with 1 and we end with infinity. Okay, so I'm not really sure what to do. Let's just start with k equals 1, and you end up with sine of pi. Then let's let k equal 2, and you have sine of 2 pi. K equal 3, but again, we'll be here a very long time. Sine of 3 pi, if we, again, just keep going. Notice that the sine of pi is 0, the sine of 2 pi is 0. So I'm pretty confident that my sum is 0, even though, again, we haven't really learned about an infinite sum yet. Or sum of an infinite sequence, I should say. This is actually an infinite series, and we're going to learn about that in just a little bit. And the infinite series converges to 0. So we haven't really learned about that yet. We're going to have to explain more later, but let's look at the next one. Go ahead and pause the video and try something similar and see if you can find out what's going on with part E. Our index of summation started with k equals 1 and ended with infinity. So again, more on this later. But if you let k equal 1, k equal 2, k equal 3, k equal 4, look at this. We have a sequence that we're finding a sum of a sequence of numbers. And if you have 3.3 repeating, the infinite series converges to 1/3. Okay, let's take a look at number 2. As we're talking about Carl Friedrich Gauss. He was able to add the numbers from 1 to 100. So it's a very old tale about how his classmates were still copying down the problem. He walked up to the teacher's desk and said, "There it is." The teacher did not believe him. She thought, how could he possibly, I think she wanted a little break or something. She thought it would take the students a while to complete this task, but he completed it right away. So what's important is how he did it. So some of you might have heard that what he did was he added the numbers from 1 to 100 twice. So he considered from 1 to 100 and then adding from 100, counting down to 1. Realizing that you would have 101 100 times. So 100 and ones, but then he realized he wanted to add 1 to 100 once, so he divided by 2. So again, he had the answer right away. So this is actually helping us with how we might find the sum of the arithmetic sequence. Notice he took the first term and the last term, added them together, multiplied by how many terms there were, and divided by 2. So here we go. So we have, and I summarized right here, some formulas for arithmetic to find the sum of arithmetic sequences, and here are our formulas to find sums of geometric. We haven't talked about infinite yet. So go ahead and read the blue boxes and take a look at the formulas, and then we'll proceed. Go ahead and pause the video. Okay, sorry, I don't have a fun story for the geometric sums, but let's go ahead and do some examples. So if I want to find the sum of the arithmetic sequence, notice the first term is 10. The common difference is 2, so you can get, generate a few terms if you want. And notice that the nth term is 28. The problem is we don't know how many terms we are adding. So the first thing you have to do, since it's arithmetic, I can use this formula that we've learned for arithmetic sequences. Let's consider the nth term is 28. The first term is 10, the common difference is 2, and we need to find n. We need to decide how many terms are you adding. So we are trying to find the sum of 10, the first 10 terms. Now you could use either formula. Why don't we try the one that we talked about with Gauss. So the sum of the first 10 terms is 10. And then you add the first term and the last term. And that's 190. What I would like you to do is consider part B and attempt to use the other formula that we learned. Go ahead and pause the video and give it a try. The first thing you need to do is find how many terms you're adding. So if the nth term is 33, we need to find n, so use your explicit formula for arithmetic sequence, and we find out that we are adding 13 terms. So if I use this formula, I have the sum of the first 13 terms in this particular arithmetic sequence is 975. Notice that this particular formula we actually could derive from the first formula that we use, because if you replace a sub n with the explicit formula, you end up with n over 2 times the quantity 2a sub 1 plus d times the quantity n minus 1. Okay, so what we're going to do now is we are going to think about a geometric sequence, and we are going to use the formula for the sum of the geometric sequence. So first of all, notice this is one number. So we need to figure out how many terms would we be adding together. So I could use the explicit formula for a geometric sequence. The common ratio is -11, so if the nth term is u, and the first term is -1, the common ratio is -11, we need to find n. Now you could use logarithms, or when you divide by -1, here we go. And also if you use logarithms and you have some negative numbers, that might be confusing, but don't forget that n is an integer. Okay, so we could just kind of, not think about the negative with the 11 if you wanted to, because again, we know that we have some natural number for n. So I think what I would do though is I would just kind of, use my calculator and think 11 to what power is 2, 1, 4, 3, 5, 8, 8, 8, 1. That didn't even take me very long. It's 11 to the 8th. And I guess I'm not even thinking about the negative sign right now. So if I know that 8 is n minus 1, n is 9. And again, you could have thought of it with the negative sign if you wanted to, but we're looking for a natural number. So n is 9. So I want to find the sum of the first 9 terms. The first term was -1. I'm using this formula right here. 1 minus -11 to the 9th power over 1 minus -11. Now we probably should practice using our calculator, but I think that's for another time. If you type this in, why don't you go ahead and pause the video and see if you are able to use the calculator to get the correct answer. And if not, like I said, we're going to be practicing more with how to type this into your calculator. But you should get negative 196,495,641 is the sum of the first 9 terms. Example number 5, it looks a little different. Notice that I gave you the last term, but it looks a little different. And I do notice that this is geometric, and our common ratio is negative 1/3. So if this is the first term, notice I didn't multiply by negative 1/3 yet. Notice this would have to be the 11th term. So you could use the formula to figure that out, or you could just look at it and realize, oh, I multiplied by negative 1/3, the common ratio 10 times, it must be the 11th term. So if we wanted to find the sum, we could use the formula. So the sum of the first 11 terms is 4, that's the first term. 1 minus the negative 11 to the 11th power. Sorry, it's not negative 11. That was the last example. The common ratio is negative 1/3. So if you, again, type this into your calculator, you get 3.000, oh my goodness, 16935. So here's what we're going to talk about next. What would happen if I wanted to describe this using summation notation? Go ahead and pause the video and see if you're able to describe this sequence of numbers, or I should say this is the series. Describe that as a in summation notation. Oh, I may have found a mistake. I should have said given the sum of the geometric sequence. Okay, so if I say describe using summation notation, you would say, well, I would like to find the sum of the sequence. So it might help to think of a geometric explicit formula. We know the first term, we know the common ratio. And we'll let we'll start with k equals 1 and we'll end with 11. So now this is what I think this is going to work. So what I'm going to do is just check it out. If I let k equal 1, I end up with 1 minus 1, which is 0, so 4. If I let k equal 2, I end up with negative 4/3. And again, just keep checking and you'll realize that if you check with your sequence, yes, that works. That's the sum of the geometric sequence. So here we go. I want to show you something on your calculator now. So go ahead and grab your calculator and I will show you how to use your graphing calculator to support your answer. All right, so I'm going to show you how you could use your calculator. Notice everyone's calculator is different. Now what I'm about to show you also you could use on the older models. The newer model actually has a summation feature, so you could play around with that if you want. I'm just going to show you, like I said, the feature that is offered on all of the calculators. Now, first of all, if you want to find the command sum and sequence, I actually forget where it is sometimes, but all of the commands are in the catalog. You could go to catalog, which is second 0, and they're in alphabetical order. So if you want to find something in the S's, and there are a lot of S's, you go to alpha, and then above the natural log, there's an S. So notice it will take you right down to the S's. There's a nice delay here. And then you can scroll through all the S's until you get to sum. Oh, there's sequence. We need that in a little bit. All right, so you find sum and you hit enter. And then we want sequence, so go back to the catalog and get sequence. So there's sequence. And so now we want to type in, and again, you could look at your manual, but there are a series of commands. You would have to type in the rule. So we had 4. And this is kind of a parenthesis nightmare, so go ahead and pause the video and try and type in the rule. You need the comma. The comma is above the 7. Then you would need the n minus 1 power. And then a comma. All right, I already had the x minus 1 power, so then you would do a comma and you would do the variable, which we're using x. Then a comma, which is above the 7. And then our index of summation, which are 1, then a comma, and then an 11. So that took a while. If you hit enter, notice that the calculator does this for you. Now, if you hit second enter, you could get what you just typed in back. So what we're going to do now is we're going to make that 11 something bigger. Let's keep making it bigger and bigger. How about 20? And hit enter. How about 30? And hit enter. And what you notice is if you keep making that that number larger and larger, this sequence of the sum of the sequence or the series is again converging or approaching 3. So, and that's what we're going to talk about next. So let's say that we consider an infinite series. So like I just showed you, we kept changing the 11 and made it higher and higher. So let's think about what's going on. The numbers, the sum approached a value of 3, and we're thinking of this as a limit. So we know that the limit of negative 1/3 to the n is 0. So that's why if we think of this as a limit, we know that the sum is approaching 3. So by using limits, we can make sense of expressions in which an infinite number of terms are added together called infinite series. A sequence is an arrangement of numbers in a particular order. A series is the sum of the elements in a sequence. So again, go ahead and read the blue box about an infinite series. Okay, and an infinite series is not a true sum. For example, 2 plus 2 plus 2 is 8. If we add an infinite number of 2's, we do not get a real number. So to explain infinite series, we can consider partial sums. So let's consider example number 5 as an infinite geometric series and think about the sequence of partial sums. So again, you could add part of the sequence together, like we did, where we said n was 11, and then we let n be 20, and then we let n be 30, and it approaches a finite limit of 3. And that's why the series converges to 3, and the sum of the infinite series is 3. If the limit of partial sums does not exist, the series diverges and has no sum. So we need to think of some other examples. So let's take a look at some examples for number 6. Which of the series appear to converge? So what we're going to do is look at partial sums. So if you have 0.1 plus 0.01, that's 0.11. If you have 0.1 plus 0.01 plus, I should say 0, plus 0.001, we have 0.111. If we have 0.1 plus 0.01 plus 0.001 plus 0.0001, we have 0.1111. So notice that if you keep thinking about partial sums appear to be approaching a limit of 0.1 repeating, which is 1/9. So the series converges to a sum of 1/9. Why don't you pause the video and try something similar for B, C, and D. Considering partial sums for part B, we had 30, 60, 100. Notice these numbers increase without bound and have no limit. The series has no sum. The series diverges. For part C, when we think of partial sums, we had 1, 0, 1, 0, etc. Notice that these numbers oscillate and do not approach a limit. The series has no sum. The series diverges. Go ahead and pause the video and consider part D. So for part D, notice we had sums, we had partial sums. We had 3, then 2, then 0, then -3. Notice if you kept going, you would be adding more negative numbers. You would end up with numbers that decrease without bound, do not approach a limit, so this series diverges. So again, if a series converges, we say it has a sum and it converges to that particular number. And if the series does not have a sum, it either increases without bound or decreases, there is no limit, or it oscillates, there is still, this series would have no sum, so we would say it diverges. So that makes you think, will an arithmetic series ever converge? Thinking about an arithmetic series, you might say no, because for example 5, and if your common difference is 5, something like that, and you would say, well, it just keeps getting larger, or this in part D it got smaller. However, consider the series 0 plus 0 plus 0, where the common difference is 0. This series is not arithmetic in the usual sense, but it does converges to, the series converges to 0. Okay, so we're going to do one more example. We're going to talk about, well, I should say number 7 has a few examples there. Excuse me, we're going to talk about convergence of geometric series. So go ahead and pause the video for a minute and take a look at that blue box. We're saying that an infinite geometric series will have a sum if the common ratio is between -1 and 1, but not 0. and we could use this formula. So let's just take a look at some examples. For the first one, for part A, I think it helps if you generate some terms. So let k equal 0, and you get, let's see, 3 times 2, so that would be 6. Then we'll let k be 1, and let k be 2, etc. So we generated some terms. So notice we could have a common ratio of 1/2. So since 1/2 is between -1 and 1, but not 0, we can use the formula for to find the sum of an infinite geometric series. The first term was 6. The common ratio was 1/2, so we end with 12. So you could say that this series converges to 12. Go ahead and pause the video and try part B. So for part B, I generated some terms just to help my eyes a little bit. I said the index of summation was 1 to infinity, so let k equal 1. I get -1/2, let k equal 2, 1/4, etc. So looking at this series, we realize the common ratio is -1/2. That is between -1 and 1, but not 0. So I can use the formula. And I know that the first term was -1/2, and the common ratio was -1/2. So I ended up with a series that converges to 1/3. There was a sum. Let's think about part C. Go ahead and generate some terms. Pause the video and find if there is a sum for part C. To help my eyes a little bit, I went ahead and let k equal 1, let k equal 2, etc. I generated some terms. Notice that the common ratio is 3/2, which is greater than 1, so this series diverges. It increases, the sum will increase without bound. Okay, when you look at part D, did you notice that it wasn't infinite? So it actually makes no sense for me to ask you if it converges or diverges. It's not an infinite sum. It's not a sum of an infinite sequence. So we could find some terms if k is 1, if k is 2, and if k is 3. So this one actually has a sum, and the sum is 2 plus 4 plus 8. The sum is 14. Lastly, for part E, it is geometric, and the common ratio is 1/2, so we can find the sum, and we realize that the first term is 1 and the common ratio is 1/2, so the series converges to 2.